Greetings, my name is Víctor Galvis and my partner Santiago Guzmeguarin. We are students from the Universidad Nacional de Colombia. We will present the effect of phosphate-based recycled concrete aggregate treatment on the deterioration of steel reinforcement. This presentation is part of the corrosion project within the Semillero de Investigación en Ingeniería Circular para la Construcción at the Universidad Nacional de Colombia, Medellín, campus located in Antioquia, Colombia. Also contributing to this project are Diana Gómez Cano, Daniela González Betancourt, Jean Paul Arias Jaramillo, and Sebastián Meneses.
Background: the construction sector has a significant environmental impact, producing 3.9 billion tons per year of general waste, of which the 70% is concrete waste. Therefore, a solution is proposed to extend the lifespan of this waste by using it as aggregates to replace natural aggregates, which make up the 80% of concrete's composition. To use this waste as aggregates, they need to undergo a crushing process. The resulting product contains cement paste adhered to its surface, approximately between 25% and 60%. This cementitious paste contains portlandite, a calcium-rich chemical compound that includes hydroxide. Due to the presence of this other cementitious paste, the recycled aggregate has high levels of porosity, up to 3 times higher than natural aggregates. This porosity requires more water, leading to an increased water-cement ratio, which directly impacts the mechanical properties of material, specifically its compressive strength. As a result, these aggregates cannot be used for structural purpose. To counteract this increased water requirement, the pores of the recycled aggregate must be sealed, immersing the aggregate in a solution of DAP, that is diammonium phosphate, plus water, has shown significant results in reducing porosity in the aggregate's morphology. This is because portlandite, a form of calcium, reacts with diammonium phosphate, producing hydroxyapatite, sealing the pores and reduce absorption and increase compressive strength in mortars and concrete, providing optimal conditions for structural use of the aggregate. Following the research line, the effect of treated recycled aggregate on reinforcing steel is being investigated. Method: in this study, 1 inch long and 3/8-inch diameter steel bars underwent a polishing process to remove potential oxide layers. The objective was to analyze the effect of 3 solutions containing the main expected compounds in treated recycled aggregates on reinforcement steel bars. The preparate solutions were DAP plus water, CH plus DAP plus water, and CH plus water. DAP represents diammonium phosphate. CH represents calcium hydroxide, and this compound simulate the effect of spec treatment recycled aggregates, either separately or in combination. In this case, DAP plus CH. Steel bars were exposed to these solutions through immersion, and both the initial pH and initial mass of the solutions were measured for subsequent analysis. Bar exposure was evaluated at 4 different ages: 1, 5, 14, and 28 days. At each age, both the pH and bar mass were re-evaluated. Bars that reached their exposure age underwent additional analysis to identify expected minerals, specifically those belonging to the apatite family. Raman spectroscopy results reveal peaks indicating the chemical compositions formed on this steel bar surface. Phosphate compounds formation were found, which, if it is present in high concentrations, can act as agents that enhance steel corrosion. Additionally, apatite family formation was detected, a compound that densifies steel microstructure and function as strong inclusions, reinforcing the steel matrix, and inhibiting corrosions. Formation of iron oxides were also identified, specifically hematite, a common oxide that can accelerate corrosion under conditions of high humidity and carbonatation. Optical microscopy was used to observe the mineral deposits formed on the steel bar surfaces. White deposits associated with the apatite family and reddish deposits related to iron oxide can be distinguished. pH solution analysis and bar mass analysis were also conducted. In pH analysis, DAP and DAP plus CH solution show no significant change in pH levels during the first 2 exposure age. However, on day 14, both solutions experience a slight pH difference, followed by a stabilization. In contrast, the CH solution did not show abrupt change, maintaining stable pH levels through the exposure time. Mass change analysis revealed variations over the exposure time due to the mineral deposit generation and eventual solubilization of them. Results obtained through Raman spectroscopy and optical microscopy provide valuable information about the chemical compositions and mineral deposits present on reinforcement steel bars. Additionally, the analysis of pH change in solution and bar masses offers insight into the evolution of chemical process and their potential influence of the corrosion process. Conclusions. By Raman spectroscopy and optical microscopy, formation of the expected minerals from calcium phosphates were found. The minerals that arise from calcium phosphate, in this case apatite family, favor the densification of the mine structure and inhibit the corrosion process of the reinforcement steel. Phosphate compounds have an use as inhibitors of the corrosion process. However, phosphates in high concentrations could act as an electrolyte, generating pores in the steel and accelerating the corrosion process. Iron oxides were found. These oxides could work as a protective coat at first. However, depending on the environmental conditions and their concentration, could accelerate the corrosion process. Electrochemical impedance spectroscopy analysis is required to see the corrosion rate in treated RCD mortar concrete system.